Hi, I'm Daniel and I came in peace from the real-time Linux kernel community to present you the paper Demystifying the real-time Linux scheduling latency that I did in collaboration with Daniel Casini, Romulo Silva de Oliveira and Tommaso Cucinota. Well, real-time Linux is not a new topic. It's been around for more than a decade now, and it was successfully applied in the industry, for example with the Red Hat Enterprise Linux for Real-Time, and in academy with Latency and SCHEDeadline. Well, despite of that, defining Linux as a real-time operating system can be the starting point of a very warm discussion. And that's because there is still a gap between the way that Linux is analyzed as a real-time operating system and how the real-time analysis is done in theory. Linux was not designed to be a real-time operating system. Instead, it was adapted to become one. And this evolution was made basically using an experimental approach where tools were developed trying to show that Linux had a more predictable timing behavior, but without trying to define the worst-case scenarios. This is clearly a simplification of what real-time means in the theory. In the theory, a system is defined of a set of variables that describe its timing behavior. Then the analysis is done in such a way to prove that the worst-case scenario is known and is bounded to a given time. So, why don't people try to use such approach for Linux? Well, the answer is that Linux is really complex. Some assumptions made in theory, such as that the tasks are independent and that the operations are atomic, are not valid in Linux. And this creates a lot of complications on the definition of the timing behavior of the system. And together with lots of hacks that we have inside the kernel and the fast pacing of the kernel development creates a real challenge on trying to apply the real-time theory on Linux. Trying to address this problem of the complexity of Linux, in our previous work we defined a formal model that deterministically defined the behavior of threads from the viewpoint of a ECRTS developer. And this model was developed with the constant feedback from the Linux kernel community. One of the main goals of the ECRTS thread model is to serve as intermediate step between the Linux kernel code and the real-time analysis. And that's how it's used here. It is the starting point of this paper. This paper leverages the thread synchronization model from the ECRTS, translating a set of formal generators and specifications into a more natural language format that is then used to interpret the Linux behavior from the scheduling standing point. From that interpretation, we define a set of variables that precisely describe the behavior of the scheduling latency, but still using a dialect that is very close to the one used by Linux developers. And we use these variables to define a safety bound for the scheduling latency. Then, the tracing features of Linux are extended in such a way that we can extract the values for these variables that are then later used in the analysis of the safety latency bound. Finally, we do a comparison of the results of cyclic test and the proposed tool of this paper. So, going deeper on each of these steps, in the first step we leverage the thread model. The model was built upon two, let's say, abstractions, the generators and the specifications. The generators are the independent or the minimal operations that we have on the kernel synchronization. For example, we have the preemption disabled and preemption enabled generator, or the IRQ disabled and IRQ enabled generator, and the set need resched one, which is a single event generator. These generators are then translated into a set of operations in this natural language format. These specifications are the set of rules that coordinate these independent operations. For example, we can say that it's a necessary condition for the set need reset to happen that both IRQs and preemption to be disabled. And the same is valid, for example, for the context switch. It's a necessary condition for the context switch to happen that IRQs and preemptions to be disabled, but also that the task is in the scheduling context. The specifications are then translated on a set of rules of the system in the natural language format. Then, based on these arguments, we define what is the scheduling latency, which is the longest elapsed time between the instant time A in which any job of a given thread becomes ready and with the highest priority until the instant time F in which the scheduler returns the execution, letting the thread to start running its own code. In other words, we can also say that this is the instant time in which the system notes the first necessary condition for the need reset to happen until the end of the scheduler execution that returns the control to the highest priority thread that was just scheduled. We also differentiate two causes for the scheduling latency. We consider blocking as the delay caused by the currently running thread that postpones the new highest priority thread. And we consider the interference, the workload added by the IRQs and the NMI that also postpone the starting of the new highest priority thread. We started by defining the bound for the blocking, and we do it using a specification that bounds the synchronization events from the set need reset, which is the event that notifies the arrival of a new highest priority thread, until the context switch in of the new highest priority thread. Then we upper bound this blocking by selecting the first necessary condition for the set need reset to happen as the first event, and the undo of the last necessary condition for the context switch to happen, which is re-enabling the preemption after the execution of the scheduler. Then we translate the specification into a timeline format to help us in the argumentation of all the cases that we can have in this process. Then, aided by the timeline, we can easily demonstrate all the possible cases that we can have on the blocking. Finally, we worked on defining a set of variables that could be useful both to explain this bound and to be used as a reference by the developers. These variables are the POID, which means the longest delay in which the preemptions or queues are disabled to postpone the scheduler, the PSD, which is the longest window in which the preemption is disabled actually to run the scheduler, and the PAIE, that is the transient state between the preemptions being back enabled after the end of POED and getting disabled to the starting of the PSD section. Finally, we have the DST variable, which is the scheduled tail. The DST represents the unlucky case in which the processor is already scheduling a new thread, and the interrupt that will notify the arrival of the new highest priority thread needs to wait for the end of the scheduler execution to be handled, and this will cause at the end of the scheduler a new execution of the scheduling code. And then we can place these variables into the timeline format and also add the amount of interference that we can have from interrupts and NMI into the blocking. And voila! with that all stated, we could find a safe bound for the scheduling latency, including all the possible worst cases. The formula is composed of the maximum value between the DST and the POID plus the transient state from these variables to the scheduler execution and the execution time of the scheduler itself, plus the interference from the IRQs. As you can see, the interference from IRQs and NMIs were delegated to functions. And the reason being is that there is no single way to characterize the arrival of the interrupts and NMIs. So instead, trying to figure out a single way, we decided to try many different characterizations and use them to say what could be the hypothetical latency using those IRQ characterizations. And any user will decide which characterization better maps to the real systems. To make this work also practical, we developed a real-time scheduling latency estimation tool that we call RTSL. It's based on perf and it traces all the events used in the thread model for the preempt-RT. The tool works on two phases. In the record phase, it traces all the system and saves the data. And in the report phase, it analyzes the saved data, reporting the latency output. The challenge in the record phase is dealing with the high frequency of the events that are generated by the kernel. So we developed an in-kernel module that parses the trace, transforming them into information. The information is the value for the blocking variables and the execution of the IRQs that are later analyzed. The analysis of the trace is done on a second phase. It parses all the trace data and reports the potential latency that a system can have. It has two outputs, the text and the graphical one. The text output prints the values of the blocking variables and also explore different IRQ characterizations, printing the hypothetical latency that a system can have on that setup. The graphical output plots some charts using matplotlib that's useful for comparison of the different IRQ characterization, and it's also useful for papers. It's also worth saying that the tracing infrastructure built in this paper can be used to define the root cause of the latency, fixing a well-known problem of cyclic test. And finally, we reach in the experimental part of the paper. In this section, we tried R2 comparing its result against cyclic test, running both in parallel. We run this scenario on two systems, a workstation and a server, and we try to vary some parameters like the duration of the experiments and the workload that the system was running. It's worth saying that it's not a goal of this section to try to define the worst absolute scheduling latency that the system can face. Instead, it serves to demonstrate that R2 can find latency bounds faster than cyclic tests, but also without damaging the latency itself. And we do this by comparing the RTSCAD latency results with cyclic test and also measuring the cyclic test results against itself while tracing or not tracing the system. It's nice to see how, even though Linux was developed on a purely experimental way, the determinism was always there. The thing that was missing was the analysis. The analysis was not that simple though, because we had to develop a formal model before trying to explore all the cases, giving the assurance that we found all the possible paths. It's also nice to see that our tooling is able to define the latency and define the root cause of the latency without impacting too much in the performance of the system. And finally, even though our tool finds worse latency values than cyclic test, for the vast majority of the cases these values are still under 1 millisecond, which justifies the usage of preempt-RT on a very large set of cases. And that's all. I hope to see you again in person in the next conference. Bye bye.